Um, okay, recording in progress. We will describe in this webinar the developments of the project interTwin from the point of view of the software stack, which is able to support interdisciplinary digital twins. What do we mean by this? A digital twin is a digital model of an intended or actual real-world physical product. So the system is composed of the digital counterpart for practical purposes regarding simulations, integration with other systems, testing real data, maintenance, monitoring, etc. So what we do in interTwin, we speak about digital twin engine, which mainly refers to the software component part, including perhaps also components related to automated data processing that sometimes are in the data repositories themselves. So the digital twin engine is, in the end, a software stack that is able to orchestrate complex data flows, provides access to the computing and data resource needed, enable services such as simulations, data fusion, machine learning, etc. And here in this slide, you have more or less what we consider from a very high level view, the components of a digital twin. There is hardware, data management, middleware, and software. The project is very ambitious from the point of view of the design and the engineering. We aim at co-designing and implementing a prototype for an interdisciplinary digital twin engine. This is exactly the challenge, because different sciences have different requirements and also different ways of work and different way of communicating this work and cooperating, etc. So our approach is to develop an open source platform based on open standards, offering the capability to develop application-specific digital twins. And for that, we have a large spectrum of use cases, which is indicated here to the right, related to climate, to draft prediction, to high energy physics, etc. So this, you can find a lot of information on the webpage. It's a very interesting reading. The benefits of our approach, as I hinted, one is collaboration, which sometimes is not easy because we tend to speak different technical languages, but the development effort, etc., will bring some unification, hopefully, and modularity. Let's say the solutions will be customizable according to the specific use case and needs. We are not developing, let's say, a monolithic piece of software, but many pieces of software that can be put together like a puzzle and have the digital twin work. This is a broad overview of the consortium. We are close to the end of the project. We finish end of August, so we are really finishing the last developments. The project has 30 participants. It's coordinated by the AGI Foundation, and this is the type of consortium we have. Technology providers, computing and data resource providers, and scientific community representatives. This is a high-level view of the digital twin engine architecture. We are in the middle, right, at the DTE Core, where we have the main building blocks of the core system as identified in the preparation of the project proposal. We have quality and model verification, workflow composition, and real-time and data acquisition and processing. For all these capabilities, we have products. Some of them were pre-existing, and we are developing them further to support digital twins, because this was not the original intention of these components. One is the infrastructure manager, the software and data quality validation platform, OSCAR, etc. So the other set of components is more related to the workflow support, OpenEO, which is an application programming interface to support and manage this, Ophidia, which is also an open source solution, mainly developed in the context of the climate community, and iProf, which is an open source service to support provenance. Out of all these components, these ones that are a bit colored in blue are actually an outcome of of the project. Some of them have been extended significantly, like iProf, and in other cases there are different products that have arisen from the previous ones. Yeah? So in the remaining of this webinar, we will see first iTwin AI, which is will be explaining how machine learning capabilities can be exploited and in resources from the project. We will see all the real-time data acquisition processing afterwards, and then finally the quality model and verification. Yeah. So I will stop sharing, and then I'll leave the floor to Rakesh.
I think Matteo will start, so then I will just continue.
I will start sharing. Let me know when you can see the slides. You see them?
Please put the slideshow.
Can you see the slides?
Not in presentation mode.
No, okay, yeah, sure. Okay. Yeah, all right. We can see them. All right, so let's get started. So iTwin AI, as we said, it's part of the core engine of the digital twin engine. And of course, which relies on the data lake and the computing, which are the infrastructural part, and interfaces with the users through, let's say, a platform. So what is the component we're developing? Actually, this component is targeting AI workflows and method lifecycle. And we are actually developing this component, which is called iTwin AI. And the core features focus on distributed machine learning and this machine learning training and distributed hyperparameter optimization on HPC and cloud resources. The goal is to support both PyTorch and TensorFlow frameworks to help the scientists to track provenance information through YProv, but also exploiting popular frameworks such as MLflow to deploy and provide a machine learning models registry to store and version and keep models that can be retrained in the future. Of course, we are interested in making a link with infrastructure, both through Rusho and other libraries for distributed computing. And to close the loop in orange, we of course provide an interface with the users, which is both through a command line interface, but also a Jupyter like interface. So as I said, one of the key features is machine learning at scale on HPC. When we talk about distributed machine learning training, we actually think about a data parallel distributed machine learning, which means that the whole data set is partitioned and each worker is associated to a different GPU, and in each is working on a specific partition of the data set. Here in the middle, you can see, for instance, a scaling test we ran some time ago on JSC on up to 512 GPUs, where we were interested in studying the overhead that iTwin AI introduces, and where we empirically demonstrated that iTwin AI is not introducing any considerable overhead. And on the right-hand side, you can see an example of energy benchmarking study in which we are interested in analyzing how different distributed frameworks that we are using under the hood impact the energy consumption of the workload. Another aspect is distributed hyperparameter optimization. So here you have let's say schematics of how it would look conceptually. So the goal is to exploit in the most efficient way HPC resources to try in parallel as many hyperparameter configurations as possible. On the right-hand side, you can see a plot with different loss values, loss functions. I mean, actually loss values. And as we can see, in the yellow line was actually the loss function obtained with some hyperparameters suggested by some use case developers, whereas the green line is what we were able to obtain through hyperparameter optimization, which resulted in about 74% of improvement over the validation loss, which is quite important. Other aspects, as I was saying, are the connection with the infrastructure. So we're using the interlink component, which I guess was presented in a previous webinar. And the goal is to use interlink to transparently offload tasks from cloud to HPC using containers. So containers are the common language. And since the containers are the common language, and for us, it's very important to provide a consistent way of building them and integrating them in our CI/CD workflows. So we had a talk at KubeCon on this. Whereas on the right-hand side, you can see an example of how Jupyter Lab containers that we are building can be used to offload and the computation to HPC and create an interactive session on an HPC compute node through interlink. Here, I will just briefly show that we were actually also able to offload an entire array job, which was launched on cloud using the kubeRay operator to HPC. This was again done in collaboration with INFN and using interlink. And at the moment, the integration with HPC centers is mostly done with Vega, on which we were able to, let's say, also use interlink to offload tasks and jobs, such as Jupyter Lab, also accessing Rusho, the Rusho data lake, and but we're also working on JSCs, on Julish, especially on the Jewel system, where we are currently, let's say, developing most of our code. Now, another important aspect of iTwin AI is the concept of tracking machine learning logs and doing it in a way which is user friendly to the end users. So in iTwin AI, we've been developing this logger abstraction layer, which basically allows the users to always have the same code but still be able to access different logging frameworks, such as MLflow, Bayesian biases, and TensorBoard, without having to change their code. And this also allows us to integrate new loggers, such as the YProbML, developed by the University of Trento, which is a logger that provides functionalities such as tracking provenance information from the training environment, from the execution environment on which the experimenter is actually running the training. Another important aspect, I was mentioned before, is the machine learning models registry. So by deploying an MLflow server, we're actually enabling our users to store the models during training, store different checkpoints, different versions of their model, and retrain those models and reuse the models in inference in their digital twins. So yeah, here we can see an example of how users can actually manipulate and manage the models. Now, during our work, we've been collaborating a lot with the use cases, and so at some point we came up with this question. So how can other scientists and researchers benefit from the integration work that has been done so far, and how can they actually reuse the code that has been developed during the integration of these use cases with as little prior knowledge as possible, in terms of benchmarking, for instance, or comparing the model that they're developing with some other use case from iTwin AI? Well, that's how we came up with the idea of plugins. So we can say that iTwin AI, starting from the left to right, so iTwin AI is a Python library that provides a toolkit for tools for distributed training, for loggers, we were seeing before. Pipeline, it's something that pipelining, let's say, something I didn't have time to show. Hyperparameter optimization. And then on top of these components, the use cases can actually build domain-specific components, such as trainers, data generators, data preprocessors, and so on and so forth. But then third-party, let's say, users like external researchers can also build on top of this ecosystem, reusing existing components from iTwin AI, from a use case developers, but also developing on their own, some additional components. So that's how, and all of these can be made possible by the concept of plugins. So before leaving the floor to Rakesh to actually see some more specific example on how a plugin is actually being developed, I want just to cover 2 examples. First one is let's say AI-based model for hydrological modeling to produce early warnings for droughts, developed by URAC. And in this case, we have an LSTM model that was integrated in iTwin AI, and we were able to run distributed training and hyperparameter optimization. And now the code is being ported into this plugin. You can visit at this link. Another example of plugin that comes from the physics world. So high energy physics. This is another use case. We have an interTwin, which is focusing on AI-based fast simulation of particle showers in vectors, in calorimeters, more specifically. So the goal here is to generate a GAN, is to train a GAN, a three-dimensional GAN, which is able to speed up Monte Carlo simulations. And also, in this case, after the integration with iTwin AI, we packaged the code into this plugin, which can be found at this address. On our documentation page, you can find a more detailed list of all the currently existing plugins, which span, again, from physics sciences to environmental sciences. Not all of them are interTwin use cases. So just also to show that there is some more, let's say, uptake even outside of the project. But yeah, please feel free to visit this page. In practice, using these plugins means, let's say, pip installing them. So once a plugin is installed by a pip, it will become available directly under the iTwin AI package. So it will be possible to be imported as it was actually called part of the iTwin AI package. But without further ado, I will then leave the floor to Rakesh, who will actually show us how, an integration can be done in more details. So I don't know, Rakesh, if you want me to keep sharing.
Do you? Yeah. Maybe you can just continue with your share. Yeah. Thanks, Matteo. Basically, I will quickly show an example of one of these integrations, just to give you a flavor of how this looks like. Of course, this is sort of quite simplified in that sense. But anyway, I hope this gives you some broad overview of how it looks like. So this is an example of this package called NorFlow. It comes from the latest QCD community, developed by our collaborators from ETH Zurich and CSIC. And so that's on the right, you can see the package itself. So the NorFlow package, which is open source. So yeah, of course, if you would like more details on the use case itself, there are much more details in the repository, and also there is a deliverable from interTwin, which is also available for more details on this. But anyway, I just put here a few points on what it does, just to let you know what is going on. So there is So it's a method for, as it is called, normalizing flows to have sort of a generative model for the lattice field theory. Yeah, how this works is basically it learns some complex distributions through a series of various simpler, let's say, transformations of simple probability distributions. And in order to build this so-called model, which you see in the bold letters, you need these three inputs, which are the prior, which draws the initial samples, the neural network, which does, let's say, this invertible transformations, and the action, which sort of is the target to which you want to fit your prediction to. So these are the three components which are needed for, yeah, let's say, running this particular model. Next slide, please.
Okay, so, sorry, I was probably a bit frozen. Is this now
Okay,
next
yeah,
one?
no, yeah,
Okay.
no problem.
Okay.
Yeah. So as I said, you have on the left here the model, which has these three components, so the prior, net, and action. And this was, let's say, the initial setup of the use case. So you have on the there is of course much more code which is there, but I just show the parts which are really needed for the integration. So on the left is the model where you specify these tree networks, and on the right is the fitter, yeah, so which is basically sort of the trainer, which specifies all the training logic, doing the forward and backward steps and things like that. So you can see with the red highlighted box, there is this device handler, which was already there in the initial setup, which calls this distributed function class, where you can see a bunch of steps. So there is some sort of initialization step for handling the distributed training. Then there is some seeding, yeah, and then finally destroying of the process group itself. So this was basically the code which came from the use case. This works fine, but the point was that this is restricted to one of the strategies. So how do we actually go ahead with the integration? I show here very simply. So you have this new fitter now, which you see in this box, which inherits from this torch trainer, which is provided by ITwin AI. And now the strategy code basically is handled entirely through this flag. So you see the red box, it's a DTP strategy. Can you click again, Matteo? Which basically gets all the logic from one of these classes. So you in this example, you see three different classes. So one is DTP, then hoverboard and DeepSpeed. So basically for all of these classes, we have defined the methods which are required to, let's say, run a training with one of these chosen strategies. So the advantage here is that for the use case itself, they don't really need to care about all this logic, but they just need to specify this as a flag. So this is an example only for the strategy. The same thing goes for the logging, for instance, which Matteo was showing, also the profiler, for instance. So all of the logic is easily handled through calling this torch trainer class, which wraps everything. So now, yeah, Matteo, next slide. So how does a training pipeline look like? So Matteo was mentioning about pipeline here. So this is an example of, let's say, how we handle the training in ITwin AI. So we use these so-called configuration files, which allow, a sort of a centralized control of all types of hyperparameters. So you have basically for this particular use case, three examples, three different categories of a definition, which goes into this configuration file. So you have the configuration itself, yeah. So like the hyperparameters, you have learning rate, batch size, things like that. On the middle panel, you have the definition itself. So you can see these three models which are required for the model class. So you have net, prior, and action. And on the right, you have basically the pipeline definition. So you specify there the flow of information. So first, for instance, needs to initialize a model, then the config, and yeah, things of that sort. And also here you specify, for instance, the strategy, as you can see. And then the launching itself is quite simple. You can this is an example of how this would look like. And yeah, next slide. And how does this go back to the plugins which Matteo was showing? So this is an example of another plugin. So for this use case itself, we have developed also a plugin which then allows the use case to independently work on their source code. And the environment creation is easily managed through this, in this case, through pyproject.toml file. So Matteo was showing with pip install, you can get these dependencies. Can you click again, Matteo? No. Yeah, okay. Yeah. So yeah, basically I show you here an example of this PyProject toml file, and if you look a bit more closely, you can see that the dependencies are specified there, which includes not only IT AI but also the non-flow based packages which need to be installed. So as you can see, this is quite straightforward and requires, let's say, very minimal effort from the use case side to an integration. So that was a quick summary of how this looks like. I think that was the last slide from my side. Yeah, So then probably we can open up for questions now.
There was one question in the chat asked by Adnan Kribi, who asks, does it include a specific MLOps tool, or how do you pronounce it, or does it integrate with tools like TensorBoard and others?
TensorBoard, you can.
Exactly. So the goal is not to invent yet another tool, but to integrate with existing ones. Let's say the only advantage, potential advantage, is that you can, once you're using this abstraction layer, you can easily switch between them. So we didn't want we didn't want to force the users to either go for MLflow or for TensorBoard, because they may have different requirements, or they just may be more used to use either one or the other. So the idea is just that once you use this logger, then you're automatically using TensorBoard or MLflow or any other under the hood.
Okay, so I think if there are more questions, we can take it at the end. And now we can move to the next. Thanks a lot, Matteo and Rakesh. And we can move to the next components to be presented by Estebalis and Miguel.
Thank you, Andrea. I'm going to share the presentation. So yes, we are going to present the components that these are core modules in the DTE digital twin engine in the project of interTwin. We are going to present infrastructure manager, Oscar, and Diseneos. Infrastructure Manager and Oscar are platforms that have been developed in the UPV a while ago, and Diseneos is a new tool developed entirely inside the interTwin project. And Miguel is going to give us more details about the Infrastructure Manager. So I leave the floor to him.
Okay, thanks, Estivalis. So yes, commenting the Infrastructure Manager, it's a service that enables the deployment of virtual infrastructure on top of cloud resources. It uses the infrastructure as a code paradigm. It has two different languages. It can use RADL, that is the native language of the Infrastructure Manager, but it currently mainly uses Tosca, that is an OASIS standard, in order to describe cloud topologies. And then the IAM automates the deployment, configuration, monitoring, and data of the virtual infrastructures. It supports a wide variety of cloud backends, thus making the user applications cloud agnostic. Thanks. The infrastructure manager has several features because it enables the deployment of any virtual platform with the precise configuration required by the user. It allows to deploy any kind of complex virtual infrastructure. And as we are using this infrastructure as a code paradigm, the infrastructure descriptions are text documents that can be easily shared with different users. It does not need to use prepackaged virtual machine images, so you can use any vanilla virtual machine image using an Ubuntu or CentOS or any Red Hat-based virtual machine image. And it enables that the very same complex infrastructure can be deployed on-premise or in a public cloud provider. In order to interact with the IAM, it has a web interface that is publicly available in this web that appears in the slide. It's integrated with EGI checking for authentication and also with EGI APPDB in order to get information about the cloud providers in EGI and the list of virtual machine images available. So it enables to deploy virtual infrastructure with a set of clicks for non-advanced users. It had a set of curated Tosca templates that has been extended in the project, adding new big data analytic tools that I will explain a little bit in the next slide. The IAM dashboard is with a light composition of templates in a way that you can combine several tools that can be deployed together. And this service is part of the services of the EGI catalog. So these are the list of the main big data analytics tools that have been deployed within the project. In the slide, you have the links in order to see the Tosca template for each of the tools, and a link to access the IAM dashboard in order to deploy any of the tools. All these tools are composed not only by a Tosca template, but also with an Ansible roles that performs the configuration of the selected tool. And you can deploy it on your own cloud provider, or you can use it in order to deploy in a public cloud provider if you don't have access to a previous one. And it has also a set of input parameters that enables to tune the configuration in order to adjust to the user requirements. So here you can see a set of screenshots of the IAM dashboard. It has an easy interface because it's designed for non-advanced users. All the templates that are shown there are described in Tosca, but it is not shown to the user. The user only sees a set of forms where the user has to add a set of input parameters, a set of clicks, and finally to get the deployment, the infrastructure deployed. In this YouTube link, you can see a full demo of how to use the IAM dashboard in order to deploy an infrastructure. It also has a REST API in order to access it programmatically. It follows the Open API specification. And in these links, you have information about the API, and also have the Swagger description of the full API in order to make it easier to interact with the IAM service. And this is the last slide from the infrastructure manager. So please, Estíbaliz, follow with the rest of components.
Thank you, Miguel. I'm going to talk now about Oscar. Oh, I forgot to tell you that you can ask questions using the Q&A box. So Oscar is an open source serverless platform for event-driven data processing and is deployed on a Kubernetes cluster. It has a multi-tenancy support, and the authentication can be done via EGI check-in or keycloak. Here you have the URL to the Oscar documentation, and it has also a blog where you can see some use cases. And this image is an overview of the architecture of Oscar, and you can see the different components. It has a MinIO instance deployed along Oscar inside the Kubernetes cluster, and also a native for synchronous invocations. And the fast supervisor is a component to provide access to another storage systems like the cache, OneData, etc. And this deployment can be done very easily using the infrastructure manager. This would be the step-by-step process of deploying an Oscar cluster using the IAM. And it can be deployed on premises, public and federated clouds, and also on devices like Raspberry Pis for edge computing. It's scalable and employs the Clues software that has been also developed in the UPV, so it can scale in and out depending on the load. It has flexible interfaces, so Oscar can be, you can communicate with Oscar using an API REST, a web interface, and a command line interface, and also a Python library called Oscar Python. It supports multiple storage backends like MinIO, Amazon S3, OneData, or any storage service using the WebDAV protocol. The event-driven part is done through DTE Neos. This is the data connector tool that I will talk a little bit more later, that allow us to create these Apache NiFi data flows. And some of the supported sources are the cache, Amazon S3 through Amazon SQS, and Kafka for real-time acquisition. Oscar is a container-based tool, so you can create your own container containing the tools that you need, like libraries, scripts, dependencies, etc. And you provide that container and the script that is going to be executed inside that container, and very easily create an Oscar service. So every time the user uploads new data to the storage is going to generate an event that is going to trigger an Oscar job. And that is, in the end, is a pod inside a Kubernetes cluster. This diagram shows the status of Oscar before the interTwin project, where you can use the deployed MinIO instance to trigger new jobs. But here I show you the new diagram where you're using DTE Neos. You can create these Apache NiFi data flows that are going to allow Oscar to be invoked by some other data storage solutions like Dcache, Kafka, or Amazon S3. And here is a list of the integrations that we perform through the interTwin project. First of all, I'm going to talk about this integration that we did using DTE Neos and for Dcache, this distributed storage solution. Like I said, the DTE Neos is the data connector through Apache NiFi for Oscar. Manages the creation of these data processing flows very easily from a YAML file using a command line interface tool. And Apache NiFi is built to automate the flow of data between systems. So what we did was building this automatic data flow to monitor the cache and be able to trigger OSCAR services when a new file is uploaded to the cache. This is the YAML file. We need to provide the Apache NiFi credentials, the input source configuration, in this case for the cache, and the destination configuration. In this case, is a very simple service in OSCAR, and the connection. So to define that relationship, we use this DCNews command. And this is going to be deployed on our Apache NiFi instance. That, by the way, is also deployed using the infrastructure manager along with OSCAR and MinIO. So the execution of this data flow could be like this. First, the user creates an OSCAR service, then creates the NiFi data flow using the DCNews tool, and NiFi begins to monitor the cache for events. So once the user uploads new data, like for example, this input file that contains this text, NiFi is going to capture that event and is going to trigger an OSCAR service, and OSCAR is going to run the job. So then OSCAR uploads the output to the cache, and in this case is a simple service that is going to format the text that receives, and the user can download the output. In the second integration that we did, we used the interlink project, also developed inside the interTwin project. Is developed by the INFM and provides an abstraction for the execution of any Kubernetes pod on any remote host supporting containers. So with this tool, we could, from OSCAR, delegate pods to HPC supercomputers. And all of this is transparent for the user. Here we have a detailed diagram of the demo that we performed using the iTwin AI tool, already presented by Matteo and Rakesh. This tool contains an AI pipeline, and since it can be containerized, we can also create an OSCAR service for that. So basically, the user creates the service, the NiFi data flow using DCNews, so it can monitor this storage system. In this case, it's also the cache. So once the user uploads new data, OSCAR is going to create a job that is going to be cached by interlink, and that job is going to be offloaded to the HPC supercomputer. In this case was the Vega supercomputer in Slovenia. So there, the fast supervisor, this is an OSCAR component, is going to download the data from the cache, and the data is going to be processed inside the HPC cluster, and the result is going to be uploaded to the cache again for the user to retrieve it. Here you have a YouTube video with the demo. We also managed to deploy Jupyter notebooks and perform some MinIO integration in them, so you can easily create an exposed service, so you can access from your OSCAR cluster to this Jupyter notebook, and this Jupyter notebook is going to mount the MinIO bucket, so you can trigger services that you can be also deployed from your Jupyter notebook. In this video demo, we show you how we managed to execute CWL workflows from a Jupyter notebook that was deployed using this OSCAR functionality. We also deployed the Deltares use case. This was the digital twin flood use case, and it's used for detecting flood hazards and their impacts. It's composed by several models like WFlow, Sphinx, and Race. Here you can also see a demo with execution, but basically this is the diagram. So we developed this CWL file containing the different steps for the Deltares use case. For each of the steps, we can check the OSCAR cluster status, we retrieve the status and prepare the OSCAR services. If the OSCAR services are already deployed, then we continue to the next step. We upload the data that is going to trigger the OSCAR, the appropriate OSCAR service, the one for WFlow, Sphinx, or Race, and the output is going to be generated and retrieved again from the CWL automatically. We also developed this use case integration from URAC. They are using the Hydroform for drought forecasting. Here you can see a demo of the execution. In this case, we are using a Python script. It was executed step by step in a Jupyter notebook for interactive to provide interactively some parameters like the authentication tokens. And the steps are very similar, but in this case, we employed input data directly from Amazon S3. And lastly, we've been advancing OSCAR with Rusio for large-scale scientific data management. Rusio is an open source data management system created by CERN to store and manage scientific data. So we've been able to add Rusio support to OSCAR. So it's integrated into the fast supervisor. So Rusio can be employed as input and output source. And we've been working on this proof of concept for the event-driven part. So storing some data into Rusio is going to notificate OSCAR to trigger a service. So here you can see more or less the proof of concept that we did. So Rusio employs a RabbitMQ to notify the events, and we can capture those events and filter them using an Apache NiFi data flow in order to invoke the appropriate OSCAR service. So as conclusions, during the interTwin project, the infrastructure manager has enhanced deployment capabilities by enabling the creation and management of virtual infrastructures on top of cloud resources, and developing Tosca templates to facilitate the automated deployment of big data analytics tools, providing researchers with quick and seamless access to advanced data processing environments. Additionally, the development carried for OSCAR and DCNeos has enabled to improve interaction with data, both in data lakes like Bcache, S3, and Rusio, and real-time acquisition like Kafka. Access to external computational resources like HPC supercomputers via Interlink, integration of interactive tools for DTE development like Jupyter notebooks, and execution of I2I, Deltares, and URAC use cases. Thanks for the projects involved. Thank you very much. And this is the team that we've been working on these tools. Thank you, Miguel Caballer, Sergio Langarita, Caterina Alcón, and Germán Molto.
Thanks a lot, Estebalis and Miguel. So I don't know if there are questions. but which we can also take at the end, as I mentioned before. If not question for now, we can move to the next speaker, Alexander. Thanks again, Isabel.
Yes, you just need to stop sharing so that I can take over.
Miguel, can you please stop sharing so Alexander can continue? Okay.
Okay. Great, and let's continue. So I will present the next component here then, which is OpenEO that we use for data fusion in this project. OpenEO has been in development since quite a while already. It's in itself the outcome of an Horizon 2020 project, which has been run from 2017 to 20 under leadership of Technical University of Vienna. You can find a lot of information also on the website there on the general concepts. Here in interTwin project, we have a group of core developers ranging from the EODC, the Earth Observation Data Center in Vienna, ourselves as EURAC Research, and also the University of Münster included. And the core idea of this tool is to really let the researchers focus on the design of your algorithm, the analysis you want to do, the workflow around that, and keep away all the complexities that you have when needing to deal with the infrastructures themselves. So very similar to what we've heard before also in the talk of Matteo regarding iTwin AI and also of Estivalis. The goal here is really to let the people focus on the analysis, the research, and not be bothered with all the infrastructure management and adapting code to specific environments and so on, but rather have an abstraction layer in the middle that allows for more simplified description and also for platform independence of where you run and execute your workflows. OpenEO, also as the name says, is focusing here on Earth observation, data processing, so mostly gridded data sets coming from satellite imagery, climate data, and all kinds of mapping products. It has a rich ecosystem of tools around it. It's based on an API, open API for interaction with it, and users can use various means then of utilizing the API, either through different client libraries available in R, Python, and JavaScript, or even for non-programmers through an interactive web editor where you can just create your workflows in a model builder, basically. It's the most complete Earth observation processing API that is out there. It allows for supports a lot of different parts of the processing chain. It's finding the data that is there, authentication with the services, the data processing itself, the management of the workflows, and of course also the export and sharing of the results, all by allowing to use different types of clients with different types of backends, so to really have a high level of interoperability, very independent of the environment that things are running and completely transparent to the user. So these backends can be something running in an HPC or in a cloud service. They can be based on more high-level services through APIs or directly built on the file system. OpenEO always allows you to interact with the data and the processing capabilities and the backends themselves. There are multiple implementations out there also based on very different programming languages, ranging from Python environment on top of Xarray and Dask, but there's also other environments working on the Spark cluster for the processing, so very different software stacks that are supported here already. All of this is, of course, also open source and accessible for everyone who is interested in this. The core of OpenEO lies around a set of predefined processes. We went down this round mainly to have a high level of interoperability so that the user can rely on a rich set of functions that are available in all the implementations. And then people can develop their own higher level processes, which are basically constructed from these predefined processes, and share them with others again as so-called user-defined processes, which is just a combination of the granular core processes and built on top of that. Sometimes if there are new ways of workflows or tools that are needed, it's also possible to include own custom scripts in form of user-defined functions currently supported in R and Python code, as to extend the functionality where there's not already a predefined process available, basically. Here are just some examples of this. So there are more than 100 different processes defined for these predefined processes. And on the left-hand side, you see a very simple way of calling a user-defined function, which is basically handed over either as a text or by linking to a source online to invoke the execution of this environment. All of the processing in OpenEO is conceptually a DAG, a directed acyclic graph, which can then be represented graphically as seen here. Below this is always a JSON document which contains a description of this graph, and this is what also is exchanged between the clients where you build your workflows and the backends, which then receive this graph object to interpret the steps and things that they need to do in order to do the data processing. This includes important things like loading your data, specifying an area of interest, for example, in form of geographic coordinates, time of interest, the time when you for which you are interested to do the data processing, and then some actual functions to do the processing. In this very simple example, all the graph does is load some data, it stores this again. That's another thing which was at the core of OpenEO from the very beginning, to be independent of data formats. So the user can, in the end of a graph, define how the results should be presented based on the needs that they have in terms of file formats, for example. In interTwin, the core focus here is, of course, on the data fusion aspect, which really prepares the data for processing in the different digital twins. This means that we can source data from different sources. This raster data might come in different grids, map projections, resolutions, and so on. So before being able to pipe this data into a model, they need to be harmonized, aligned, possibly filtered for the specific area of interest that is needed, or the time range. Also available features or data variables that are in these data collections, and in this way prepare the data for machine learning models so that they can rely on a consistent and complete data array when doing the training and prediction of these models. Here we see, for example, the use case that was already mentioned before for the hydrological forecasting, specifically looking into drought events. Here we rely on some of the software tools that also our project partners from Beltaris have built and wrapped them into containers, which allows to execute them in different environments, as seen in the previous talk, also, for example, through Oscar, then run and use them. There are many different data sets that are involved in this processing. So we need to make sure that that all of these different data sets can be aligned and fed to the models in order to do the analysis of the drought model. So in terms of the integration, we are building new processes in OpenEO right now so that that they can call also Oscar. So the Oscar client will basically baked in to an OpenEO backend to be able to call directly Oscar and then trigger the processing there, and in this way create a seamless graph from the user perspective, and comes with all the nice features that Elise has previously presented, so that a user can run the execution in cloud or HPC environment and does not need to know how to specifically manage HPC cluster with GPU nodes, but can just request the right resources for the processing job that is needed there. In this handover, we also make sure that all the data comes in the same metadata models through stack collections that describe how the data is organized and where the data assets are located and can be loaded into the processing chain through web requests. Here you can see a very simple workflow, for example, then to load the data through the stack collection or directly from a file system, to apply the pre-processing, then in the request to Oscar, provide the stack catalog that has this data from OpenIO pre-processed. Then the execution can be linked to some of the Docker containers that we have seen before, for example, the one from Wflow for the drought forecasting, but it can also be the machine learning workflow where we build a surrogate model, which is then using iTwin AI, which again is called from Oscar to then do the actual machine learning training phase, or later then also the inference phase, making use of the offload functionality through interlink when needed, so that also GPU nodes and the HPC can be used, and finally ship back the results through a stack catalog and allow further processing in OpenIO in the most simple case, just storing the results, but also here after the modeling, other things can be done for example, visualizing the maps in a more interesting way and then store the final results, basically. So in conclusion, OpenIO allows us the seamless integration of Earth observation data in these digital twin workflows. One important thing is here also that we conform as much as possible to international standards with respect to geographic data management. The core tools that we use here, OpenIO and Stack, are both currently also in final approval, becoming OGC community standards. OGC is the Geospatial Consortium. And the pre-processing of the EO data for modeling workflows is a core part that we work on here, which allow both physics-based models and data-driven models to be used, as well as integration, both of them in the surrogate model approach, as we have chosen for our use case here in the project. So this was a very quick overview of what OpenIO is doing in this project. Thanks a lot, and if you have any questions, feel free to ask them or also come back to us at a later point. Thanks a lot.
Thank you, Alexander. And I don't see questions, but as I said, we can come back later if you have. So we can move then to the final talk on SQS. Thanks again, Alexander. And now Ivan is on the floor.
Hello, my name is Ivan Palomo, and I'll be talking about the SQS quality framework. First of all, we'll talk about what's SQS, the criteria that is used in order to evaluate software, the different modules, and what do we offer. And we'll end up talking about use cases and future developments. First of all, what is SQS? SQS translates to Software Quality Assurance as a Service. It's a platform that aims to bring novel quality practice to developing software in research environments, because following these quality conventions boosts adoption, usability, and sustainability in order to achieve steady innovation. In order to evaluate to evaluate the software, we follow different evaluation criteria. We want to promote accessibility. We want the source code to be accessible as a public resource. We want documentation. We want to ensure that the important documents related with the code are present. We want licensing. We want to resolve the legal aspects related to source code reuse through the presence of license files. We want static security. We want to protect by helping detect insecure patterns when writing code. We also want to foster readability of the code by following certain style standards, and so on. In order to evaluate all of these different criteria, we are powered by open source tools. For example, for style, for each different programming language, we have a different tool that allows the software to evaluate. For example, for Python, we have Flake8, for Java, we have checkstyle, for JSON, we have JSON link, and others. Something similar happens with fairness, which we have two fairness evaluators, the FairEva and Fuji. But in the case that, for example, your code is not supported, you are not writing in a language that is supported, there is a streamlined support for new tools. First of all, you need to set up the environment for the tool, basically find a Docker image that is able to run the software that you're interested. Then you need to add the tool details in the SQS tooling metadata, basically specifying the Docker image, the different arguments that the tool might need, and the quality assurance criterion that you want to check. And finally, you might need to create a small plugin in order to parse the output of the tool in order so that SQS can understand what the tool is saying. In SQS, we present two modules for two different audiences. First of all, for a more of a developer use, we have the Pipelines as a Service module, which offers developers with graphical means to compose continuous integration, continuous development pipelines that carry out software verification and validation automatically. And then we have, for a more of a general use, for a more of a badging use, we have the quality assessment and awarding module, which analyze the level of compliance with a set of standards for software. The first module, the Pipelines as a Service module, offers developers with these CI/CD pipelines without the need to permeate down to complex technology solutions, which can be difficult. We deliver these pipelines that, without too much effort, allow the developer to continuously evaluate their code in order to bring it up to better quality standards. In order to create these pipelines, you have an interface which allows you to select all of the criteria that you want to evaluate, and for each one of those, exactly what tool you are interested in. Then you can evaluate your software at your own pace. If you are just interested, for example, in style and for a Python code, then you might go to QC style and add Flake8 or PyCode style, depending on which one you are interested. Then once you have chosen all of the details, it will automatically create the files that you need to add the pipelines to the repository that you want to provide them. That way, whenever the user wants, for example, after each push, the pipeline will be triggered and the code will be evaluated. Then you can download those files, and there are different features that we provide, such as making a pull request to add that pipeline directly to your repository, or just try out the pipelines and check the results in our servers. Let's go to the other module, the quality assessment and awarding module. We want to, as we said before, stimulate the presence of good practices to ease the adoption, reusability, and sustainability of the code. So we provide assessment data, including quality assurance reports and bid logs, so you can trace the quality during the development life cycle, and also digital badges that contribute to crediting and reputation building. In order to access this module, there are two different ways. There is first a more programmatical approach. We have a RESTful API that you can access and create the pipelines and run them all the times that you want. Or if you want more of a simple approach in order to just get the patch, you can go to the web portal and copy and paste your repository URL, and then you can get the full evaluation. There are 4 possible results that you can get. You can get no badge, or you can get a bronze, silver, or gold medal. In order to get these badges, you need to pass different criteria. For example, for the bronze medal, you need to pass the accessibility, documentation, and licensing. For the silver badge, you need to pass the code metadata and versioning test. And finally, for the gold badge, you need to pass all the style tests, the security static analysis, and unit testing. These criteria, all of them have different levels of criticality, and not all of them can always be automatically evaluated. Some of them require user feedback for a successful perfect evaluation. Also, SQAS is integrated with co-hosting platforms such as GitLab or GitHub that then you can do quality assurance work at development time inside the platform where the code is being maintained. This reacts to events triggered by the hosting platform such as pushes, changes requests, etc. It features already existing CI technologies such as GitHub Actions and GitLab CI. It provides a reporting summary for each build and allows for dynamic badging updated as the assessment progresses. Then SQES has a role in digital twin projects, is part of interTwin, and fills in the quality assurance building block during the development and operation phases of a digital twin. The quality assurance and fair assessment of individual digital assets while the digital project is in the development phase, and then also the integration with workflow management system and scientific data management technologies during the operation phase. Now let's see the use cases. There is one with interTwin climate change, which is the validation of the biophilia workflow description documents. These workflow documents are JSON files that need to have certain structures, need to have the instructions in certain orders and different specifications. So if we have this use case dev who wants to push this JSON file into the repository, which will be stored for in the future to be used, whenever the user pushes this document, it will automatically trigger the SQAS in order to evaluate that file and make sure that it's a good file, that it has all the things that it needs in order to be used. Then you can also, another use case is to train the models statically with a small test set. We have this machine learning training workflow that has produced this model. So before or whenever you are uploading it to a machine learning model registry, such as MLflow, you can, with a small inference container and a minimal test dataset, you can evaluate it in order to make sure that it has certain qualities. More use cases and future work is that you can integrate it with workflow management systems in order to do quality assurance during the execution of a workflow. This time, the integration will not be coded, will not be through events, but coded in the specific workflow. You can do this in order to, after the ingestion phase, in order to ensure data integrity and data deduplication, or you can do it after the pre-processing the data in order to ensure format consistency and fairness. It can also work with data management systems, making quality assurance work on data, reacting to CRUD operations on dataset repositories or lakes. Thank you for listening to me, and I'll be glad to ask any questions you may have.
Thanks a lot, Ivan. So we now, okay, there are some backup slides which I don't need, I think. But we are now at the end of the webinar, so we have some minutes for questions from the audience. So either you can use the Q&A, or you can raise your hand, and we can also listen to your question directly. So if you have question, now is the time. And if you don't have questions now, you can also reach out anytime and to the speakers directly, or to our LinkedIn page, for any information and for any question, of course, you may have later. Okay. If there are no final questions, then I think that we can close a little bit earlier. would like to thank again all the speakers today, and we can. I would just want to mention that we will have also two final webinars in June and July related to the digital twin application. So the final version at the end of the project of the both physics and the environmental DTE application pilots that we are finalizing now. And as mentioned, we will have the recordings and the slides available for anyone. Thanks again to the speakers and to the attendees, and talk to you soon. Thank you.
Thank you.
Thank you.
Thank you. Bye-bye.
Thanks.
Okay.